Hello juniors, today we're going to see the concept of conditional probability, which is something that you have also studied last year, but we need to see this before moving on into more deep concepts. Okay, so conditional probability. The objectives for today's class are four. Number one, use of Venn diagrams, true diagrams, and space diagrams. Number two, identify and calculate combined events, mutually exclusive events, and independent events. Then define and apply conditional probability, and finally find probabilities with and without replacement. Okay, so let's see the concept of conditional probability through the example which we were studying during all of the different concepts we've seen. So it says, here's the Venn diagram showing students who do archery and badminton. So we have archery A, badminton B. If we know that a particular student does badminton, how does this affect the probability that they also do archery? So this is basically the concept of conditional probability. And it says, altogether, 30 students do badminton, right? 16 plus 14, 30. Of these, 16 also do archery. We write the probability that a student does archery, given that they do badminton, as probability of archery, given that, the vertical line is given that they do badminton, okay? So, if you take a look at the graph right here, if we say, what is the probability of a student doing archery given that it does badminton? Basically, what we're doing is we are reducing our universe to people who do badminton, right? Because we say a probability of students who do archery given that they do badminton. So this is like our new universe, okay? So our universe of people who do badminton, because we know for sure that the student does badminton, is reduced to 30 people now. Okay, so in this new universe, the red circle, which would be our new universe, how many of them do archery? So the number of people who do archery are only this, which are 16. So the probability would be 16 out of 30, okay? So that's the concept of conditional probability. It's reducing our universe to the given or known condition of the problem, okay? So here it says probability of A given that B is equal to the probability or the number in the intersection, which is 16, divided by our new universe, which is the whole badminton, which is 30, right? So this is the probability. This is known as conditional probability since the outcome of A is dependent on the outcome of B. Okay, so here it explains with numbers, but it's the same thing. Okay, then it says, in general, for two events A and B, the probability of A occurring given that B has occurred can be found using this formula. So it's the probability of the conditional probability is the intersection between the two events, the probability of the intersection divided by the probability of the particular event that we are given as a fact, as something known, okay? Then it says rearranging this formula gives probability of the intersection equals probability, the conditional probability times probability of B. That's just if we take this term multiplying up here, we're getting that formula. Okay, this formula is always in the formula booklet. If you take a look at the formula booklet, you'll see that here you have conditional probability and it's written exactly in the way it is shown in the electronic assignment. So we have seen all of these different types of events and of, different types of events, conditional probability, mutually exclusive events, conditional probability, and independent events. And we have also seen the basic concept of probability and what complementary events are. Okay, so we have seen all of those different concepts already. Let's go back. Then we have something very important, which is kind of intuitive. It says if A and B are independent events, then the conditional probability, A given that B, is equal to the probability of A directly. And the probability of B given that A has occurred is equal to the probability of B. And the probability of A given that B hasn't occurred is equal to the probability of A. And the probability of B given that A hasn't occurred is equal to probability of B. Why are we saying this? we're saying that A and B are independent events, right? So if they are independent events, remember the concept. The concept of independent events say that we don't care what occurred before. It will not change the probability of the next occurrence, right? That's why this this happens only if A and B are independent events, right? The probability of A, given that B has already occurred, does not change, right? If we put as an example the example of the coin, I'm going to write it here, example, flipping a coin, you would say that, let's say that event B is getting a head, right? And probability A is getting a tail. So if I already got a head, so B has already occurred, does it change the probability of getting a tail? And the answer is no, right? Because they are independent events. So the probability is still remaining the same. We don't care about what occurred before. And that's what it says here. Recall that for independent events, probability of the intersection is equal to the product of the probabilities. By definition, for independent events, A and B, the probability of A occurring, given that B has occurred, will equal the probability of A occurring, since A is not affected by the occurrence of B. So that's exactly what I just explained. Okay, so let's see one example where we're going to apply the concept of conditional probability. This is still very simple. We're going to be getting into a more tough problems later on. It says, of the 53 staff at school, 36 drink tea, 18 drink coffee, and 10 drink neither tea nor coffee. How many staff drink both tea and coffee? Okay, so to solve this problem, the best thing we could do is first do a Venn diagram to see what's happening, right? So in this case, we should have two circles, right? One for tea, one for coffee. And then the people outside are the one who drink neither. So we have our universe, the universe, and two circles. One for tea and another one for coffee. So this is tea, this is coffee. Okay, so we can only plug in this value, which is people who drink neither. We know that neither would be outside of the two circles, so that's 10. Then we know that 36 in total drink tea and 18 in total drink coffee. We don't know how many people are in the middle, so I can call this x. If this is x, tea would be 36 minus x, and coffee would be 18 minus x. And we know that in total, our universe is equal to 53. So with this information, we can find the value of x. We can say that the total, 53 people, must be equal to all of the sum of all of the elements, right? So 36 minus x plus 18 minus x plus 10. And that is equal to 53. So then we solve for x. We see that we can simplify some terms, this one with this one. Then we have 53 is equal to 18 plus 10, that's 28. 28 plus 36, that should be equal to 64. 64. Yes, so 64 minus x, right? Minus x. So then if we solve for x, we're going to take the x to the other side. So this is 64 minus 53. So x is equal to 11. Okay, so once we have our value of x, we can rewrite all of our terms. We know that this is 11. So t only would be 36 minus 11, which is 25. And then 18 minus x would be coffee, which is 7, right? Okay, so once we have all of the information, we can start solving the problem. Part A says, how many staff drink both tea and coffee? Okay, so that's what we just found. 11 drink both, right? We can write it, let's use mathematical notation. The number of people who drink both tea and coffee is equal to 11. 11 people. Okay, you see that when I want to express a number, I use an N in front of the symbols, right? If I want to find probability, I would use a capital P. Okay, then we have part B. It says, one member of the staff is chosen at random. Find the probability that he drinks tea but not coffee. Okay, so we want to find the probability of a person drinking tea but not coffee. How do we express that into symbols? Tea but not coffee would be tea intersection not coffee. Remember, the word but is but and are both letters that we use to express the intersection, right? So tea but not coffee. And if we look at our Venn diagram, that represents this part over here, right? These are the people who drink tea but not coffee. It's like saying tea only, right? So people who drink tea only would be 25 out of the total, which are 53. That's our universe. Okay, so this is the results. Then we have part C. If he is a drink, find the probability that if he is a tea drinker, he drinks coffee as well. So you see that here we're given a condition. We know that this person is a tea drinker, right? So if we know something for sure, then you immediately need to think about conditional probability. So if he's a tea drinker, he drinks coffee as well. If we write that in symbol notation, that would be probability that this person drinks coffee, given that he or she, actually, the problem only talks about he, but we don't know if it only says staff. Okay, so I'm going to do it like that. Coffee given that tea, right? So in this case, our universe is reduced, right? Our new universe should be the amount of people who drink tea in total, which we know are 36, right? Here we have the information. So 36 is our new universe. And out of those people in this new universe, I'm only looking at this circle here. How many drink tea? 11 drink tea, okay? So this conditional probability would be 11 out of 36, okay? If we want to write this in mathematical notation, I'm going to take this down a little bit just to show you. This is the same as saying probability of C intersection T. This is if we apply the formula, okay? Divided by probability of T. And that's exactly what we did. 11 is the intersection between coffee and tea, and 36 is the total amount of people who drink tea. Okay? So this is equal to, I'll take this up here again, and there you go. This is the conditional probability, coffee given that tea. Finally, there's a part D, which says, find the probability that if he is a tea drinker, he does not drink coffee. Okay, so same condition. We know that this person drinks tea, but we want to find now the probability that he does not drink coffee. Okay, so it's the same thing, but now it changes that it should be not coffee. So C prime, given that T. So it's the same reasoning. It's the probability of not C and T divided by a probability of T. And if you look at the previous exercise we did, part B, we already found probability of T intersection not C. So this would be equal to sorry, this is probability. So we're only staying with this numerator, which is 25 out of our new universe, which is 36 people who drink tea. Okay, if you want to look at the reasoning behind this, if we want to find people who do not drink coffee, given that they drink tea, then our new universe is T, right, which is 36. And out of these people, how many of them do not drink coffee? 25, right? The rest do drink coffee, so it's 25 out of 36, okay? I think it's easier to reason just by looking at the Venn diagram rather than thinking about the formula, right? It's much easier. Okay, so this is the result, and that's the only example I have for this video about conditional probability. But I wanted to discuss this one last thing, which is something that I realized I didn't discuss with you yet. It's interesting. Maybe if you want to pause the video here and try to solve this on your own, it's something interesting. It says, during the mid-1600s, mathematicians Blaise Pascal, Pierre de Fermat, and Antoine Gambot puzzled over this simple gambling problem. Which is more likely, rolling at least 1/6 on 4 throws of 1 dice, or rolling at least 1/6 on 24 throws with 2 dice? Okay, which one do you think is more likely to occur? Let's analyze this through the probability perspective. I'm gonna first of all highlight the two different events to see what's happening. Okay, so the first event is rolling at least 1/6 on 4 throws of 1 dice. Okay, that's one possibility. And the other possible event is rolling at least 1/6 on 24 throws with 2 dice. Okay, so which one of this is more likely to occur, the green one or the blue one? Let's analyze each of this. In the first case, it says rolling at least 1/6 on 4 throws of 1 dice. So I'm only throwing 1 dice here, right? So the probability of getting a 6 when I throw 1 dice is equal to 1/6, right? So if I throw the dice 4 times, what will be the probability of getting a 6? Obviously, the probability should be greater than 1/6, right? Because I'm throwing the dice 4 times, so I have more chances of getting a 6, right? So how do I calculate this probability? Well, if I throw it again, I will have 1/6 probability of getting a 6. Then if I throw it for a third time, then the probability of getting a 6 is also 1/6. And if I throw it a fourth time, it's also 1/6. You see that I'm adding the probabilities here. Why am I am not multiplying? Because if I multiply, the difference with multiplying is that if I multiply the probability, the resultant probability will be much less than what 1/6, and that's not logical. And if the problem said, what is the probability of getting a 6 4 times in a row, then that would be 1/6 times 1/6 times 1/6 times 1/6. That is, if I want to get 6 4 times in a row, right? And you see that probability is much less likely to occur than getting only 1/6 in 4 throws, right? So that's why we add instead of multiplying in this particular case. So if we add this, we're going to get 4/6, which if we simplify is 2/3. And that's 66.7 or 6666 and so on % of probability, right? So it's actually a very big number, and it's logical, right? If I throw a dice 4 times, I should be able, or I should have a big chance of getting at least 1/6, right? Okay, now let's analyze the second situation. It says, rolling at least 1/6 on 24 throws with 2 dice. So we want the probability of a 6/6. 6/6. If we analyze this from the perspective of of the first throw of the 2 dice, right? If we want to get a 6/6, we should get a 6 in the first dice, so the probability is 1/6 for the first dice. But at the same time, I need to get a 6 on the second dice. So in this case, we multiply, right? Because we want to get a 6 on the second dice as well. So this is times 1/6, which is the probability of getting a 6 in the other dice, right? So this is the probability of getting 1/6. But what happens? I have 24 opportunities, 24 throws to get this 6/6, right? So this is 1 throw, but I want to do 24 throws, right? And in each of these throws, I want to calculate the probability of a double six. So basically, what I'm going to be doing is multiplying this probability times 24, which is the same as doing this. We could have wrote here 1 over 6 times 4 directly, right? So but just to show you the concept, I wrote it as a sum, as an addition, right? But we could write 1 over 6 times 1 over 6 plus 1 over 6 times 1 over 6. We could write this 24 times and we would get the same result, right? It's easier if we just multiply this by 24. So if we perform this, we would get 24 out of 36. And if we simplify this, we can divide this by 12. We would get 2 out of 3. So basically, what we just found is that the probability of occurrence of these two events we were comparing is actually the same. So same probability would be the conclusion, probability. So you see how you can think about these different situations just by applying the concept of probability, you know, right? It looks like something difficult, but it's actually not. Okay, so that'll be it for today's class, juniors. I hope this was clear. And let me see, yes. I hope this was clear. If you have any doubts, please let me know. We can cover this in future live sessions. See you.